So maybe you learned at some point in your life the dot product. The dot product is a gadget that you associate to vectors in like Euclidean space, Rn, where and what it spits out when you have two vectors, you take their dot product, and what it spits out is a number. And that number, it turns out, is deeply related to the geometry of those vectors. Maybe you learned a formula at some point in your life like this: v dot w, these are vectors, is equal to the length of v times the length of w times the cosine of the angle between them. So if you have these two vectors, okay, you take their dot product and you have this kind of setup where something like this. Now imagine that angle there, that angle theta, is a right angle, pi over 2 radians. Then that's going to cause this guy here to be 0. Well, that must mean that the dot product is 0 as long as the vectors are non-zero, right? In other words, we can use the fact that the dot product of between two vectors is 0 to deduce that the angle between those vectors is a right angle, pi over 2 radians, or 90 degrees if you like dumb, stupid units, yeah? There's something analogous, but for functions. And when we define that, and it's very natural, there's a lot of reasons to understand this as being the natural extension of the dot product, but to the world of functions. And if you carry that through, it's going to turn out that the eigenfunctions that we found, these eigenfunctions here, are orthogonal to one another. All right, so let me write all of this stuff down. Delete. Okay, so I want to talk about orthogonality. Orthogonal, just by the way, orthogonal just means a right angle. Just means right angled. Orthogonality of eigenfunctions. Okay. So here's how we're going to define the inner product. We define so I'm going to define something called the inner product. The inner product of two solutions. Well, I'll just say of two functions on the interval from a to b, like this, okay, will be the integral from a to b of f of x, or x of, let me call them x1 and x2 because that's more in line with what we've been doing. x1 of t times x2 of t dt. It's the integral of the product of the two functions, okay? And the theorem that I won't prove because I want to keep this short and sweet is that eigenfunctions for a given eigenvalue problem of type 1, 2, or 3, where by type 1, 2, and 3, I mean these three types. Okay? Eigenvalue functions of those three types are orthogonal if they have different eigenvalues. And what do I mean by orthogonal? That means that if you compute this integral of the product of these eigenvalue functions, that you get a big fat 0. That's sort of saying that the angle between these eigenfunctions is a right angle. That's the geometric intuition you should have. Now, what's heavy about this, if you take that seriously, and you should, because it's very useful, is that we have, for this particular eigenfunction, eigenvalue problem, we actually have infinitely many eigenfunctions. Two for each integer, positive integer. That's an infinite number. And I'm saying that they are all at right angles to one another. Okay? We're going to use that to be able to decompose any sufficiently nice periodic function into an infinite sum of these functions, okay? And that's the heart of Fourier series, all right? That's where we're headed. And the orthogonality of these eigenfunctions is going to come in incredibly clutch to figuring out how that all works. Okay, see you in the next one.